Hi everyone. Hi everyone. Hola, hola. Sí, hola. Hola, hola, hola. Hola, 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 hola. Hola. Vale, hola. Hi. Hi everyone. Hi. Welcome to the last session of today. Please, after this session, remain together because we are going to attend as a group to the social activity. We will meet up at the entrance of this building, like after 10 minutes of the end of the talk. Then we will go to Gregorio Marañón by walking, and we will take line 10 towards the stop of called Batán, where the Parque de Atracciones is located. So having said this, it's a great honor to have with us Carlo Rovelli. Carlo is an excellent researcher and speaker. He's currently working at the Aix-Marseille University in France, but he is moving to Madrid soon. His main research topic is quantum gravity. Actually, he's one of the co-founders of Loop Quantum Gravity. But apart from that, he has deep interest in philosophy and the foundation of quantum mechanics. In particular, he has his own interpretation of quantum mechanics, which is called relational quantum mechanics, and I admit I'm a real fan of that interpretation. And even apart from that, he has published like many books for the general public, so he has done a great labor in divulgation. So thanks for that, Carlo. And today he will give us a talk, an introductory talk, about how quantum technologies can serve as tools in order to solve some problems in fundamental physics, high energy physics, quantum gravity. So please, Carlo, stage is yours.
Thank you, thank you. Thank you very much. And it's great to be in a country like mine in which people come late. I've spent the last time the other side of the Atlantic, everybody was on time, was horrible for me because it's impossible. I'm gonna talk about quantum gravity, which is my main scientific interest. And I assume you don't know anything about quantum gravity. I know in the audience there are people who work in quantum gravity. There's Guillermo, there's Francesca, there's students, others. But I'm not talking to you guys mostly. I'm talking to the rest of you. Assuming you know very little about quantum gravity, and maybe some of you will find it interesting, but probably most of you are not going to work on quantum gravity. But there are some general, deep ideas there which I think are interested to anybody. So let me start very concretely this way. So take a shape. This is a tetrahedron, right? The shape bounded by this, hi Pascal, by this thing here. This is not a regular tetrahedron. I built it myself yesterday. I went to a shop, Tiger or something shop, and bought these things. And you can actually, well, I'm going to break it. You can either make one of these lines longer or shorter. So this has a geometry, right? It's elementary geometry. I think you all can, sit down knowing the length of that, compute the area, the volume, do the geometry of that. It's just Euclidean three-dimensional basic geometry. But geometry is math, okay? If you want to know the length of this, you have to measure it. So you have to take something, for instance, this, and start measuring. This is 20 centimeters and so on. Or in any other way. You can measure the area of this, you close it, you spray something, you see how many things are captured, that's proportional to the area. You can wrap something around it and then measure the volume by putting it in water and see how much the water weighs, and so on. I mean, they're all possible ways. And when you measure measure length, area, you're doing physics, not mathematics. Right? It's a very different thing. So I want to talk about the shape of that as is seen from a physicist who measure it, which is not about abstract theorems and deducing things, it's about measurement. So why? Well, because it's not obvious that the mathematics of Euclidean geometry correctly describe the shapes that we find in nature. And in fact, we know it doesn't for a number of reasons. Two important reasons being general relativity and quantum theory. So these both general relativity and quantum theory are going to make a difference between just Euclidean three-dimensional geometry as a piece of math and the real world, the space in which we live, all right? So in the space of which we live, we have things like that. We make measurements and we talk about the shape of that. Now, let's do it for real. So first thing, when we measure something, some length, some area, some volume, because of general relativity, because of what Einstein understood 110 years ago, 1915, his main papers, and because of the immense success of general relativity, which has been now confirmed so spectacularly, we know that the things we are measuring is the gravitational field. Okay? The length of that, when I measure this to be 20 centimeters, at the light of general relativity, so in the proper relativistic description of what is going on, not in the approximation where you forget gravity, what you're measuring is a quantity of gravitational field along this line, so to say. And in fact, for those of you who have had a class in general relativity, you know how to write the length. The length is the integral of the square root of g mu nu. I mean, if you remember it, just remember it is. If you don't, doesn't matter. The point is that the length is a function of the gravitational field. So this thing here, it's actually a measure of gravitational field. It's the analog of the things you go to the hardware and you buy the things that measure the electric field, right? Or a magnetometer. You can buy something and measure the magnetic field here. And you can measure the gravitational field here. Here it is. Why? Because the atoms inside here keep themselves at a distance depending on the gravitational field. So in a sense, they hang on the gravitational field to keep that distance. All right. So when we measure the area, the volume of things, we are measuring gravitational field. Okay, so still a tetrahedron, it's still the shape and so on. Oh wait, then there's quantum mechanics, okay? So in quantum mechanics, you all know quantum mechanics, and I'm not sure you all know general relativity, but I'm sure you all know quantum mechanics. Quantum mechanics, everything you measure, it's a quantum variable, a quantum observable, a quantum thing, right? Everything. It can be, its quantum properties can be negligible, but they're always quantum properties. So the length of this is actually an observable in a quantum theory, right? The area of this is an observable in a quantum theory. The volume of this is an observable in a quantum theory. So let me try to do it. I'll start with a little bit of technicalities. Then the rest of the talk will be much less technicalities than. But I want to start with something. Let's do this way. This is my tetrahedron. And I have the length, L1, there are 6 of them, L6. Now, we can think of writing quantum operators associated to length in some Hilbert space that describe the geometry of these things. Now, when you try to do it, it doesn't work well, so there is a little bit a better way of doing it. These are the technicalities. But please follow with me in these little technicalities because they will bring us to the quantum geometry of this pretty fast. The reason, there are a number of reasons for which these are not good variables for describing the geometry. One is that there are ugly inequalities between them, right? The length of this plus the length of this must be more than the length of this. And if you want to write this for quantum operators, it's ugly to work with it. But there is a simple way to get rid of inequalities, which is the following. Instead of maybe I have, let's do here. Instead of focusing on the length, I write 4 vectors, L1, L2, L3, and L4, which captures the geometry like the length, okay, but better. How? Well, take one face, take the normal, the perpendicular to the face, okay, and that's going to be my vector L1. Well, this doesn't tell you how long it is. Let's say that the length of this vector, so these are going to be LA, A is 1 to 4. And I want the length of each one of them to be the area of the face. Okay? So now I have 4 vectors, each one, so L1, L2, L3, and in the back, L4. And if I know these 4 vectors, I know the geometry, right? Now, I'm not going to prove it or anything, but there's a little theorem that says that if you have these 4 vectors, any 4 vectors satisfying an equation, which I'm write in a moment, there's always a tetrahedron that has that shape. And the equation is very simple. It's the sum 1, 2, 3, 4 of LA equals 0. I'm going to prove it to you that if you have a tetrahedron and you consider these 4 normals, the sum is 0. Here's the proof. It's due to Roger Penrose, last Nobel Prize in General Relativity. Imagine this is a piece of wood with this shape. Okay, put it in water and pressure the water. If you pressure the water, what happens to it? Nothing. Okay, because the forces all around equilibrate. But the sum of the forces is the normal time the area, which is 0. So here's a physics proof of this equation, which is actually true. It's a theorem by Gauss, whatever. You can prove it in all possible ways. Okay? So they satisfy this equation here. And one can prove that any 4 vectors that satisfy this equation correspond to a tetrahedron. It's a little proof in geometry. It's due to Lorentz, not that Lorentz, another Lorentz. Okay, so, okay. In gravity, each one of these things is a function of a gravitational field. Fine, it's a gravitational field here, and in quantum gravity, each one of these things is an operator. So we'll have operators, LA, 4 vector operators, okay, that describe the quantum properties of this. Now, what do we know about this? Here I have to make a jump, and this is the only jump I'm making. Well, in general, operators don't commute. They'll have an algebra, okay? What can we say about the algebra of that? Let me guess. Let us guess. And the guess is a shortcut for doing a long path, which is take general relativity, do the Hamiltonian analysis, do a Dirac quantization, write the commutation relation, and then write these operators and compute them. It's a long, long thing. I mean, ask the people sitting in the middle who have done this exercise. It's long and painful, but the result is super simple. And the result is pretty obvious. It's the following. What I'm interested in here is the shape of this. Remember, I was interested in just the length. The length are the same if I rotate this. So I'm interested in this up to rotations. So I want to describe this in a Hilbert space where I know how to rotate things, of course. I mean, I'm in space. So my Hilbert space, I want to write a Hilbert space. I'm going to carry a representation of SO3, of rotation. Suppose you all know some group theory, so it's a representation of SO3, okay? And then if you have done any quantum mechanics or any relativistic quantum mechanics, you know that one very rapidly jumps to the double covering of that, which is SU2. This is not very important. These are technicalities. It's just rotations or the double covering of the rotation group. So this Hilbert space will carry a representation of rotations. My object that satisfies this equation is going to be invariant under rotation. And it's very tempting to say, okay, this is a generator of the rotations. Okay? And it's 0 because it's describing something which is invariant under the rotations. Good. So here's the hint. The L are generators of SO3 or SU2, each one of them. So there are 4 of them. So my Hilbert space is going to be a representation of, say, J1, representation J2, a representation J3, representation J4. These are all representations, J4. These are all representation of SU2. And the general Hilbert space will be a sum of things like that for all possible value of J1, J2, J3, J4. And on this irreducible representation, J1 is a representation of SU2 with spin J1. On this irreducible representation, I know what these things are. LA is just the generators of a representation. This is a length square, this is nothing. So with some constant, L0 square. Which means that I know the commutation relation between these things. L1 vector, L2 commute, because each one is act on a different one. But L1I, L1J commutator is just the commutation relation of SU2 or SU4 is epsilon ijk. So it's standard angular momentum. Ijk, Lk. And since there is this L0 square, you have an L0 square here because these are scaled by. So now I know the quantum theory of this object. I know that these are operators, and I know the commutation relations. I've done the quantum theory of that. And now you're going to think, oh, come on, you're a theoretician, this is blah, blah, blah mathematics. Where is the physics? Here's the physics. The area is the length of this thing. Okay? So it's the square root of the product of this with itself. So it's going to be L0 square, the generator, a generator of SU2 square root of a square. But you know the eigenvalues of this quantity, right? This is a Casimir of SU2. Its eigenvalue j plus 1. So every, so that means that the area is going to be the eigenvalues of the area are L0 square j plus 1, where j is a half integer. 0, 1, 0, 1 half, 1, 3 half, and so on. That's it. I've just proven to you, with this little jump of assuming the commutation relation, a result which, if you think for a moment, is formidable. If you measure the area, remember, you can measure the area of that. You're not going to get any real number. You can only get certain numbers. Like when you do the harmonic oscillator, the energy is only certain numbers. When you do the hydrogen atom, the orbits are only certain orbits, right? You get a quantization of a quantity. Which quantity? The area. The area of thought, the area of this. Now, how big is L0, this quantity that enters there? You can easily guess, because it should be H bar. Commutator is H bar then. And I said you can derive that commutation from general relativity, from the full thing of general relativity. General relativity has a constant in front of it. This is G Newton. And H bar G Newton is a length square. So L0 is exactly H bar G Newton. Okay? length square is 10 to the minus 44 centimeters. So it's smaller than anything you can think about. But that's the prediction. This is the quanta of area here are many, 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 10 to the 40. But if this was smaller and smaller and smaller and smaller, it could not be an arbitrary shape. It could only be one of the eigenvalues of the area. So geometry is quantized in this sense. Clear? You follow? But then remember, quantization means more than just eigenvalues. Think about angular momentum. When you do angular momentum, standard quantum mechanical angular momentum, J square is quantized J plus 1. Jz, you can quantize the M quantum numbers. But if you make Jz sharp, Jx and Jy are unsharp, of course, right? They don't commute. So that means that these two quantities, the I component of one of these vectors and the J component of this, don't commute. So they cannot be both sharp. So the shape of this tetrahedron is never sharp, because it's described by quantities that don't commute with one another. So when you go into the small, you don't have actually tetrahedra. Like if you have a spinning particle, when you go into the small, it's not a spinning particle. It's something which quantizes angular momentum. So geometry is discrete and is fuzzy. In the small, you can make a state in which some of the variables described with geometry of this are sharp, but some other are not sharp, or none of them are sharp. You can make wave packets around semi-classical. So the physical space in which we are is described by a unsharp, fuzzy, discretized geometry, and the general state can be a quantum superposition of different geometries, and that's quantum gravity. So that's, I wanted to give you a short account of the core of quantum gravity, how it's described by loop quantum gravity. I've taken 20 minutes. Do you have questions now? Because then I'm going to shift gear and be much less technical and give you a more overview of quantum gravity as a general theory. Yes?
Thank you. What you just described is apparently does not satisfy Lorentz invariance in the sense that the volume depends on the reference system, the reference frame where you're moving.
Yeah,
with respect to the object. So
absolutely. So what I described here, it's measurements at a certain time, which are not Lorentz invariant, so are in a given frame. The theory as a whole is going to have to be Lorentz invariant. I'm going to mention that, absolutely. Other question? Yes. Do you want this, or can you scream?
We are supposing these vectors are in a representation of SO3. So in some sense, we are like supposing there is like a background Euclidean space.
Great question. The answer is no. And the point is the following. In general relativity, you assume that, general relativity assumes that space-time is curved, right? But it also assumes that when you go into the small, classically, you get closer and closer to Minkowski. So in general relativity, locally, you're always in Minkowski. Okay? And in fact, one way of formulating general relativity, the so-called tetrad formulation, you go locally and you put yourself in the tangent space in a little flat region. In that flat region, this holds. So this holds in the very small, so to say. When you start putting pieces of space-time together, you lose the flatness. And you see the flatness not in one way of calling these things, this fuzzy element of geometry is quanta of space. So each one is described in this way, but when you put them together, you get out of flatness. Good. So I'm going to do another 10, 15 minutes, and then we take a break, because 1 hour and a half is going to be long, and if there are other questions, I'll go through. Oh, I have the technology here. So this is my tetrahedron. This is just what I said. Physical geometry can be measured. This is measuring the gravitational fields. All fields are quantum fields, so physical geometry is quantum. This is just the few equations that I wrote it down, and the arrival point is this. The area is a constant times discrete numbers, which are these ones. So this is my picture, complete intuitive picture of a fuzzy tetrahedron, right? It's not. It's like when you want to describe an electron, like a spinning particle, but it's not really a spinning particle. So it's a funny tetrahedron. So geometry is quantized in the sense that the value, eigenvalues are discrete. These are plot of eigenvalue of the volume actually computed. These are the real plot. Operators don't commute. Geometry is fuzzy. A generic state is a quantum superposition. I'll skip this. Well, maybe I shouldn't skip this because it's your question there. You see, the full Hilbert space of the theory, which I'm not going to describe, is just defined here. It's going to be like a lot of these things attached to one another, roughly. All right. So let me start from zero now. So forget all this. This is a story. 100 years ago, exactly, quantum mechanics came in. It works for everything. It has to work for gravity. Let me be clear. We don't have an established theory of quantum gravity. We have, quantum theory works in a well-established way for chemistry, for condensed matter, for particle physics, for all sorts of things like cosmology, transistor, laser, whatever you want, not yet for gravity. So the problem is open. One way of viewing it is that what we actually know about the world, reliably, the fundamental level, it's quantum mechanics, general relativity and the standard model, and everything that follows from it. Which doesn't mean it's easy to do follow from it, but that's the basic. What is missing is the quantum property of gravity, which is the same thing as quantum property of space-time. Let me tell you about experiments, what we know about that. There are a number of theories of quantum gravity that have been proposed, and a number of experiments that we have ruled out many of them. For instance, you were mentioning Lorentz invariance. There was a time in which breaking Lorentz invariance was considered a possibility for making quantum gravity easier. It doesn't work experimentally. Experiments has ruled out. Lorentz invariant, if it is broken at the scale of quantum gravity, which is a very teeny scale, would be observable astrophysically. There are a number of astrophysical observations that show that Lorentz invariance is not broken, where you would expect it to be broken if quantum gravity broke it. There are theories like string theory that were written originally with a negative cosmological constant, and even today they're mostly studied with a negative cosmological constant. Nature has said no, cosmological constant was measured, it's positive, so another blow to another attempt. Supersymmetry is probably the strongest recent element of evidence against some possible attempt to do quantum gravity. Attempt to do quantum gravity with supersymmetry, which sort of helps, are now under great stress because, as you probably know, supersymmetry was expected by many scientists, not for the quantum gravity people in this room. At CERN, in the high energy particle physics experiment, it didn't show up. And then there are beautiful examples of observations in cosmology that might be affected by quantum gravity, which have been studied, out of which people hope to extract information about the general theory of quantum mechanics. Here in Madrid, in fact, next building, Guillermo and his group are studying cosmology, quantum cosmology. I'm spending most of my time recently to study black holes. I may say something at the end if we have time. Experiments which are now beginning, trying to see quantum gravity effects in the lab, not yet done. I might comment of this if you're interested. That's where some other piece of information may come out, especially ruling out some wild hypothesis that gravity is not quantized. All this to say that the theory on which we are working, loop quantum gravity, is still okay. Hasn't been ruled out by any of these things, and in my opinion is the strongest candidate. It's not the only one. It's the only strongest candidate about quantum theory of gravity. It is a possible quantum theory of gravity. This is the theory I'm talking about. It has a Hilbert space. This, you recognize the equation that I've written here. It has a algebra of operators, which is more rich than the simple one of a tetrahedron, which I've written before, but essentially yes. And it has transition amplitudes, which are written. If you think about quantum mechanics, one way of thinking about quantum mechanics is that you have a Hilbert space, you have operators, and then you have a transition amplitude. You say, given this state, what's the probability of getting to this other state? That's how the theory is written. These are the full set of equations, which I'm not going to go through, so don't be worried that I'm going to give you math about that. But I just wanted to show that the theory, that's the theory. That's the old theory. And let me make a few comments about this set of basic equations. First, there is no time. And I'm going to tell you why this. Second, there is no space in the sense that there is no x variable. There's no t variable. There's no x variable. There are no things, okay? It's all about processes, things happening. And these processes are not in space-time. I'm going to describe this in a moment. The space-time is the process itself. It's not happening in space-time. So you're not thinking, think what I've done. I've not described this in space. I've described the region of space itself, okay? For a reason that we'll see in a moment, it is impossible to think that there's an external observer. You have to think that the observer is part of the world, and you have always to think that you're looking at one piece of the world from another piece of the world. And as I just said, there are already some ruling out of theories. And if I get to the end, I'll tell you one possible observation already happening that might be an indication about quantum gravity. We don't know. So this was, again, the full theory. And this is the simplest. It's actually written in Spanish. I haven't written this slide in Spanish. I found it from an old conference. So that's what I said in a picture. General relativity tells us the space is curved. Quantum mechanics tell us that things are discrete. When you put it together, you get quantum gravity, and more precisely, you get, the discretization. Well, I'll just go ahead. Quantum theory fields are discrete, general relativity space-time is curved. When you put it together, space-time is discrete. Space-time is quanta of space, right? Quantum mechanics, in a sense, was born in the 1905 paper, Feinstein. He said the quanta of light. That's where quantum come from, the name, the quanta of light. So the quantum of space. And I want to stress this because it's a main idea. I just skimmed on it, but say it precisely. If you think about photons, the quanta of the electromagnetic field, we know how to deal with photons. We know how to calculation. Photons have quantum numbers. They have the momentum. If you do the Fourier transform, it's the position. So in a sense, photon is somewhere. So photon is living in a space. The quanta of gravity, they don't live in a space. They are space themselves. Intuitively, they make up space like the thread of my T-shirt make up the T-shirt. These are pictures of quantum of gravity. This is what I was saying before. intuitively, the Hilbert space is like a lot of this quantum polyhedra connected to one another, and they describe a quantum geometry. And now I come to Lorentz invariance evolution, because what I've described of quantum gravity so far is what you measure at fixed time. Okay? Now the question is, okay, so what about the transition? Again, I'm not giving you the equation, but giving you the idea. The idea is that you have a quantum state of space-time, this quantum space in the past, and you want to know the probability of a quantum space in the future. So you want to know probability of going from one to the other. And the theory gives you a calculation way for doing this probability, which is a sort of path integral formulation of quantum mechanics. You sum over all possible intermediate paths, where the intermediate paths can be thought as quantum space that evolve and multiply or get destroyed in this evolution, and you're summing over all these paths with some equation give you the amplitude of measuring something in the future, given that you've measured something in the past. That's sort of a picture of discrete quantum space-time jumping around and evolving. Of course, it's completely pictorial, right? Artistic, like to say. Since I stop a moment here, since you mentioned the relational interpretation of quantum mechanics, you all know quantum mechanics is complicated and people fight about how to think about it. I love this relational interpretation. It's particularly suitable for doing quantum gravity because what you're doing is, whoops, it's a relational interpretation. Sorry, let me go back. What you're doing is sort of making a measurement here, evolving and make a measurement here. So you're describing the process with respect to whatever happens around it. The Heisenberg cut between the quantum system and observer becomes the space-time boundary between a regional space-time and the rest of the universe. That's the key idea for making this works. I'll skip this, and I'll stop here on this slide, and then we take a little break. And then we stop for 5 minutes, I take questions, and then I talk about applications of this theory, black holes, early universe, stuff like that. But I want to end with this slide because I like this. This is sort of historical. Newton had this idea where there's a thing called space, and there's time that passes, and there are bodies that go into it. Before, for Descartes, there was no space, right? Space was just a property of the things. Things had the spatial extensions as a property. There was no empty space. Then Faraday and Maxwell introduced electromagnetics. They invented the fields. So now the bodies are not just particle, but particle and field. And special relativity teaches us that space and time we better think as a single thing, space-time. And then quantum mechanics tell us that a field is just a lot of particles, and particles are excitation of fields. So it brings together, photons, electromagnetic field are connected. Electrons and the Dirac field are connected. So it brings together the notion of fields and particle into quantum fields. But general relativity tells us that space-time is a field. That's what I said at the very beginning. Space-time is a gravitational field. So it's just all these fields that don't live in space, so to say, they make up space. When you bring everything together, in quantum gravity, you have only one kind of stuff. General covariant fields whose excitations are electrons, photons, and quanta of space, all living together and doing things together. Okay, so I stop here, gone long. I suppose let's take 5 minutes, 10 minutes break. Go to the bathroom, jump around, and then when I start, I'll take questions, and then I'll talk about the applications. Questions, doubts, complaints, everything, details. Yes.
Does this interpretation solve somehow the quantum measurement problem or gives a response?
Yeah, good. So I think that the quantum measurement problem, namely the strangeness of quantum theory, the how to think about quantum theory, what happened during a measurement, has, strictly speaking, nothing to do with quantum gravity. So there are two different problems. It's like, you know, some point people didn't understand the strong interactions, and then they were found the quantum theory strong interactions, but the measurement problem is still there, and so on. So one thing is to understand the quantum property of gravity. Another thing is the quantum mechanics as a whole is always funny because of the measurement problem. So there are two different things. Once I've said this clearly, there are some interpretations, because there are many solutions of the measurement problem. It's not that we don't know solutions. We have many. There's many worlds, there is a relational interpretation, there is a pilot weight theory, there is the hypothesis of physical collapse. There's some possibility of thinking about that. Somebody's saying, can you hear me well? Okay. Stay away from the microphone. Some of these interpretations are more friendly to some applications. For instance, pilot wave theory, the idea, the Broglie-Bohm theory, the idea that there is a particle and also a wave, right, in non-relativistic quantum mechanics. It's very nice, but it's very unfriendly to relativistic physics. Once you go to relativistic physics, it doesn't work. So in quantum gravity, I think that the relational interpretation goes together particularly well. In fact, I've worked on the relational interpretation a lot precisely because it talks well with quantum gravity. Relational interpretation is the idea that every system can be a quantum observer in the sense of Copenhagen, right? In textbook quantum mechanics, the system observer. And the relational interpretation is that every system can be an observer. So pick one system and is observer with respect to the rest. And this works very well here because you're always describing processes, and you can always put yourself outside the process and describe the quantum mechanic of that process and think that the observer itself can be described quantum mechanically by something else, and so on. So my answer is double. So strictly speaking, two different problems, and yet some physics pulls you toward one way of thinking or the other. Can somebody? Yeah, fantastic.
Hello. Well, sorry because I'm pretty ignorant in this field, so maybe my question is too naive, but
oh no, that's good. That's the best.
Anyways,
this is a worse question because I said
related to the question that my colleague did before the break. So you, in classical general relativity, you assume that you can have this local Minkowski space, and you can somehow patch together local Minkowskis and so on. And in here, if I understand correctly, you also assume some kind of locality maybe, or my question is related to if you assume these patches of space-time that are patched together and all of this, is this compatible with non-locality shown in entanglement and, for example, the breaking of Bell inequalities and all this? How can this be compatible?
Good, great. Yeah, that's in a sense, yeah, good. You know, it's a very good question. It's not a naive question at all. And it allows me to answer also better to the previous question. Everything which has to do with quantum non-locality, like EPR stuff and entanglement at distance and so on, remain exactly the same in quantum gravity. It's no worse and no better. Okay? Now, in quantum gravity, locality becomes a little more tricky because you can have sort of quantum superpositions of different causal structures and things like that. So there are additional complications. But there is no sense in which quantum gravity solve these problems? It's not, you can, EPR correlations, now understand them because of gravity. No, there's nothing to do. In fact, gravity makes things worse. Nor the other way around. So again, these are two different stories. Quantum mechanics is funny, it's non-local in that strange sense of EPR non-locality. It's non-local but not too much, right? It's non-local but you cannot send signals. And the same is true in quantum gravity.
Thank you. My question is way more naive. So
Good.
this is a genuinely naive question. And I don't even know how to properly frame it. But in your opinion, do you believe that there will be eventually a new theoretical framework that will not be based on quantum mechanics nor general relativity, but a new perspective, a new point of view, which will integrate both quantum mechanics and general relativity? What I'm trying to say is that this looks like we're trying to understand quantum gravity, and maybe there is like eventually a new theory, like for example, what quantum mechanics is to Newton's law, or general relativity to, like you're trying to derive something which maybe we need a new perspective. Thank you.
Good. So the general question is about where to look for solutions, in a sense. The strict answer is, of course, I don't know, right? I mean, I'm not God. I cannot read the mind of God. She does whatever she wants. They, whatever. But I think, my opinion, because my sense, is that we have, sometimes the problem is not presented correctly. It's not that we don't have a theory of quantum gravity. We have theories of quantum gravity. This is one. We have no way of testing the theory. And writing a theory is not easy. And let me put it this way. If you look at the past, progress has always been, fundamental problem in physics, has always been in two ways. One is new data. I mean, just you measure the spectra of atoms, just no way to get them in classical mechanics. And so you need something dramatically different. Everything just that doesn't work. So you have data that don't fit the theory. All examples. I mean, QCD was born from the data of the strong interaction, the hadron spectra, and so on and so forth. There are all sorts of examples of that. But then there's another way in which there have been major steps ahead, like Copernicus, like Einstein's special relativity, Einstein's general relativity. And these were big jumps, but based on looking at what was known and trying to fit together what was known. Think about special relativity. Maxwell equations and relativity of velocity, Galilean. Velocity is relative. And it seems that Maxwell equations contradict the relativity of velocity, right? There's a velocity in the Maxwell equations. Obviously, they contradict. So if Einstein had followed your suggestion, he would have said, okay, something completely different. No Maxwell equation. Let's change Maxwell equation. Let's change relativity of velocity. No, he believed Maxwell equation. He kept Maxwell equation as it is, and he kept relativity of velocity as it is. Velocity is relative, okay, like Galileo wanted. And he said, well, they fit together. It's just you have to think hard and find the way. So I think that's what we need to do. We have an enormous amount of information about the world, which is quantum mechanics. It works much better than we expected 100 years ago. And same with general relativity. It works much better than what expected 100 years ago. The last decades have been, nature has surprised us by saying, not, oh look, there is something new, but by saying, oh look, what you were speculating is not true. The Nobel Prizes, gravitational waves, entanglement at large distances, black holes, They're all Nobel Prizes. They're all physics which were in my textbooks when I studied in the 70s. Okay? I can't think a single Nobel Prize that says, oh, something new. The novelty is that all the speculations were wrong. Supersymmetry was wrong. Chain generativity was wrong. Modification of quantum mechanics were wrong. All the speculations were wrong. So nature is saying, look, you have the right things. Just be smarter. Okay? Like Einstein was smarter. And to be smarter means change the way you think. That's why what I like of this theory, loop quantum gravity, is that in a sense it's very conservative. Just, quantum, what you are saying. Quantum mechanics, generativity, nothing else. But look, like somebody was asking during the post to me, saying that, this has nothing to do with quantum field theory. There is no space, there's no fields, there's no energy, there's no momentum. You have to think that things don't exist in space, don't evolve in time, to think differently. I think that's, my opinion is that's the direction to go. I might be wrong, of course.
We know in quantum mechanics that time is not an operator, but instead is a parameter. But if we now consider space-time quantized, so it doesn't make time an operator in quantum gravity?
You're correct. But the reading of a clock, is described by an operator. And the step you have to do is to not think about time as something absolute, which is passing. Just think about readings of clocks and reading of instruments. Ask the thing the observables, and these are the operators. And this works. Technically it works. In fact, my old book on quantum mechanics, not the one I did with Francesca with all the recent stuff, the first part is all about making this clear. It's not my work, it's in the literature, was spread around the literature. The key idea is the following. Instead of describing how things evolve in time, just describe all what you can measure and how things evolve with one another. You have to think this way. So forget the idea of a single time variable that drives everything else, and just describe how things are related to one another. And in general relativity, you have to do that because between one event and another event, the clocks can measure different time lapses, right? If you have two watches, you keep one here and one you throw up and come down. Then the two measure different times. So between when they separate and where they join, how much time has passed? Well, depends how you measure it. So which one is a true time? There isn't a true time. There's just many times. So you need a formalism, and that's loop quantum gravity is based on this formalism, where you don't have a time variable at all. You have just measurable things, including clocks, and that circumvents completely this difficulty that you're saying, that in non-relativistic quantum mechanics, you want to make a T operator, it doesn't work. This is an old observation about Pauli, right? Energy is positive, so it's conjugate to time, so it couldn't, just the commutation relation would prevent T to be an operator. Others? We don't have much time, because time, some senses exist. So I'll just take the last short, how much we have, 10, 15 minutes, a bit more, to go rapidly through applications, because I've just given the theory, right? And let me stress the point. You don't believe a theory in physics until you have some hard empirical experimental verifications. And the good of loop quantum gravity is not that it got empirical verification. Nature has been kind to loop quantum gravity because has put alternative in difficulty. because the other ones the other alternative have found difficulties. But the effort, and I think the effort now in developing the theory, is to apply the theory and try to connect with measurement. So there are various areas. One is cosmology, early cosmology. There is a general, there's a lot of literature, large literature on the application of loop quantum gravity to cosmology. I'm just giving you a couple of general common things. Pretty generically, one finds this is a Friedman equation, the equation that tells you how the universe becomes larger and smaller and expand. And what loop quantum gravity does with a lot of, after a lot of calculation, is basically insert this black thing here, which implies that, suggests that if you go back in time to the Big Bang, you don't have a Big Bang but a bounce, right? So you have a bounce, a contracting universe that then expands, and then you can do a lot of physics around that, and you can hope to see in the CMB, which is where in the cosmic background radiation, which is a lot of information about early universe physics, traces of that, especially in this part of the CMB, the large angle things. A lot of works, a lot of hopes to zoom into anomalies with respect to the usual cosmological standard model and find discrepancy between the data and the usual cosmological model. Nothing definitive for a moment, but hope to get something else. This is calculations of it's a sketch of some calculations of what happens here when the previous universe contracts and bounces and try to do the transition amplitudes between before and after, so you see. Then there are black holes. Black holes I'm particularly keen because I've spent the last few years thinking a lot about black holes and application of quantum gravity of black holes, and this is what I want to tell you this because this is what excites me now. Black holes are how would I put it? The greatest surprise that nature gave us in the last decades, right? Nobody expected the universe to be full of black holes like it is. The black holes of a few solar masses, of 30 solar masses, 60 solar masses, 100 solar, no, yeah, maybe. But 1 million solar masses, 1 billion solar masses, so the universe, and many, many, many that nobody expected them to exist. Now, what has quantum gravity to do with black holes? This is how we see them. To everything we observe so far, quantum gravity has nothing to do with black holes. Black holes are perfectly well defined by general relativity. Everything we measure is accounted for beautifully by general relativity. It's a spectacular, prediction of general relativity, which is verified. Nothing to do with quantum gravity. But this is a metric inside a black hole. So a black hole is sort of the geometry inside. You can think at it that the horizon is here, the little sphere you see from the outside, and there's a huge inside. And as time passes, this black hole is like this huge space inside the little sphere, right? Black hole is like, in fairy tales, you see a little hat, you go inside, this huge, huge amount of space. That's what a black hole is. And if you look at the geometry, classical general relativity, as time passes, the interior of the black hole becomes longer and longer and longer and narrower. But then there is a famous singularity. So if you fall inside, you go into the black hole, you fall, you're crushed by singularity, which is this tube crashing around you. Careful. People sometimes think that singularity is at the center of the black hole. It's completely false. Okay, it's not down there. It's not somewhere the singularity. It's in the future. So if this room would be the black hole, the singularity is not here. Just wait, and we are squeezed. All the room is squeezed, and that's a singularity. So it's in the future. It's called time-loss space-like singularity. So that's a singularity here. And this is where classical general relativity doesn't work, doesn't tell you what happened, and you have to use loop quantum gravity. And loop quantum gravity allows us to do some calculation and see what happened next. Go next to the singularity, because of course, singularity is not a prediction of generativity, it's an indication of generativity goes wrong, right? You're going into the quantum regime, curvature is huge, that's really quantum stuff. And precisely because space-time is not continuous, you cannot get into a singularity. There's this granularity that at some point stops the compression. So what happened next? Well, that's what the theory predicts. You have this quantum gravity region, and then the theory predicts a sort of bounce back, sort of similar to the cosmological bounce. So the black hole becomes longer and longer and narrower, then bounces through this quantum thing and bounces back, comes back. And this later part is still there. So the theory predicts the black hole, it's going to go through this evolution, and you can compute when this might happen. And the result is that it might happen only if the throat here, the horizon, is very small, because then we're in a quantum regime, and it does become small because of Hawking radiation. I don't know if you know the basic. I mean, this is if you have a black hole there for a very long time, it shrinks, to become very small. Then what? Then you need quantum gravity. Quantum gravity is okay. At that point, you have this this bounce here. So what comes after here? The throat is very small. And look the beauty of here. It takes a huge amount of time the black hole to become very small. So if you fall in, you bounce and you fall in here, you bounce, you come out, a huge amount of time outside. But for you, who fall inside, it takes very short to get to the center, to the singularity to come out. So a black hole is a shortcut to the future. Jump to into a black hole, come out the other side, and you're in the very, very far away future. Of course, you're going to be squeezed, crushed by, you're going to die, everything, your atoms are going to, but if you could resist, you would come out in the future. Of course, general relativity is all about this flexibility of time, right? If general relativity tells you that there's more time up here than down there, but it's very minimal. If you go into a black hole, this effect is colossal. I'll skip this. I'll skip about the, this is about the, but that's, no, sorry. That's the point. So now let me get to the, last few minutes, to what I hope, and this is what I've been excited in recently, could be a hint for maybe seeing something about quantum gravity for real. This is a history of a black hole. This is some star collapsing. That's the horizon. This is the quantum jump. Then this is what will come out. This is the other side. And as I said, the black hole can start very big, but then it becomes very small. And then when it jumps, it's very, very small, and then it's very small here. And if you do some calculation, there are some arguments that says the duration of the life of this later part is called a remnant. It's very, very long. So the theory is predicting that a black hole becomes very small and then stays, this remnant remains for a very, very long time. How big? Well, you should be able to know how big. If you think for a moment, you should be able to say how big it is. Because look, it's going to be very small, right? Smallest as possible. Smallest possible is arbitrarily small. So the area of the horizon can be arbitrarily small. No, it cannot, because area is quantized. There's an area gap. There's zero area, nothing. But if there's an area, the smallest possible area is the one I gave you at the beginning. I computed it, right? Is L0 squared jj plus 1, where square root of jj plus 1, where j is 1/2. So basically it's L0 squared. It's a Planck area. So the theory predicts that there are stable particles at that Planck area, which are sort of black holes or white holes or whatever. But general relativity tells you that the area of the horizon determines the mass. So we know the mass, okay, of these things. And this is the Planck mass. And the Planck mass is exactly 20 micrograms, 14 point something micrograms. The Planck mass, which is sort of the number you get with h bar g and the speed of light, the mass you get, it's not very small, it's not very large, it's an order of magnitude that shouldn't scare anybody. Micrograms is the weight of my hair, right? So the theory is predicting that there is a semi-stable, long-living particle at that scale, 20 micrograms. If we see that thing, these teeny particles, it's very, very small, but they have a mass, and the mass can be observed, right, by their gravitational pull. They have no electric charge, no other charge, okay? Now, imagine there were many of these. If there were many of these in the universe, how would they look like? They would look like a powder, some matter, but doesn't interact electromagnetically, no charge, so it would be dark. So it's some sort of dark matter all over. And now here's the point. Astronomers see dark matter all over, right? This is the so-called dark matter. So that's one possibility. I don't know if this is true, right? I'm just telling you a possibility. Is that the famous dark matter, which is the most mysterious thing today in fundamental physics, because somehow everything else we can think that it follows from the fundamental physics we know. Dark matter, we have no idea what it is. This is an actual picture of dark matter, right? This is the bullet galaxy. The red and blue parts are computed from the deflection of light from background galaxies. So we know from their gravitational effects the existence of dark matter, and in this particular case is shifted with respect to the galaxy. So we know that there is stuff there. So the suggestion here is that maybe dark matter could be made by primordial black holes formed in the early universe that have evaporated, have become these stable things and remain there. So if we can measure them, and we could measure them, this is a recent paper by these people and me, using quantum technology for detecting particle. It's very simple. You have this, imagine my hair zooming very fast, and you have to pick up its gravitational attraction. So theoretically, just put a pendulum, and pendulum get excited. Concretely, it's very, very weak, so you need some technology, super sensitive, and the most super sensitive detectors we have is using quantum interference. You just quantum split something, and the effect on one side and the other are different. You have interference between the two branches, you pick it up. And the idea is to do it with Josephson junctions, many of them. This is just quantum technology, you probably know about that. Some of you know about that better than me. So if we could see these things flying through the sky, dark matter particles, and if we could see this at the right mass, the theory predicts the mass of these things, 20 micrograms, we would have a clear indication of quantum gravity, because that's exactly the Planck mass, and would have an indirect sort of experimental support of the theory. It has not been done yet. I hope it's going to happen soon. So I just want to fly through this to closing. I said there's no time variable, and yet the theory is predicted because as I said, it predicts how variable change one with respect to the other, not how variable change in time. I said there's no space variable because this quanta of space, this quantum microtetraeder I described, they're not somewhere in space, they are space themselves. Space emerge in the classical limit. There are no things, because what we are describing is it's stories, event, processes. Okay, measurement things. So they're not in processes are not in space-time, because the quantum process is exactly what space-time is in quantum gravity. There's no external observer, because if you think about this in the relational interpretation, not at the description of the full universe. I don't think it makes sense to talk about the quantum state of the full universe, anything like that. We're not looking at the universe from the outside. We're looking at regional space-time from other regional space-time. As I said, several theory has been ruled out, but maybe there is something that has already been observed, which is quantum gravitational, which is dark matter. It wouldn't be surprising, right? Black holes, you probably know that. I don't know if you know that. Black holes were observed in the 30s. When people started the first radio telescopes, the very beginning of radio telescopy, there was this strong signal from Sagittarius A star. Nobody knew what it was. In the 30s, for half a century, this signal was observed, and it was a black hole. Now we know very well it's a black hole. It's the one we have pictures about. And so black holes were hard to detect, but not because they were hard to detect, because they were hard to recognize. The signal was enormous. It's the strongest signal, radio signal coming from the skies, the Sagittarius A star. So the point was, oh, that's a black hole. That was the hard thing. So maybe dark matter, oh, that's a Planck scale particle predicted by quantum gravity. Okay, so this is a lot of people doing quantum gravity around the world, and I wanted to also say that there's a lot of people, the names of there are the names here which are completely not readable. These are people in the room, these ones and these ones. So there are people here at CSIC, there are people on Complutense elsewhere. There are a lot of people in Madrid doing that. So if you want to join, welcome. And I will be in Madrid in the next years. So at some point you want to talk to me, come anytime. Thank you very much. We have had a lot of questions, so we can stop here. But if there is some pressing questions, immediately you can raise your hands. Otherwise, we just one pressing question.
Just a very fast question. You talk about black holes in loop quantum gravity bounce. They do some kind of bounce. Does this solve the quantum information paradox of black holes?
Yes, completely, exactly. So the idea is that that's one of the possible solutions of the information paradox. The information falls into the black hole, and then it stays trapped inside this long living remnant and very, very slowly comes out.
So it's like the information is not lost, but it's sent to the future.
It's not lost. It comes out when the black hole is not black hole anymore. Is this remnant? That's right. The people who think in terms of holography and things like that hope that the information comes out earlier, before the end of the evaporation. I think that would contradict general relativity and quantum field theory too badly. I trust general relativity and quantum field theory when there is no quantum gravity. So I don't like that solution.
Thank you so much.
Any other question? If not, let's thank Carlo again. Thank you so much. And also thanks you all for coming. And all those who are attending to the social activity, let's meet up in 10 minutes at the entrance of the building.